Okay, let's talk about lasers. Got my little laser pointer here. First of all, the symbol on the right is the caution sign for lasers. Lasers are dangerous, they're fun, and we're going to learn all about them. So let's get started. First of all, the word laser is actually an acronym. We just don't capitalize every letter because we've gotten lazy over time. It stands for Light Amplification by Stimulated Emission of Radiation. Now, what the heck does that mean? A whole bunch of big words. Hopefully by the end of this presentation, you'll understand exactly what all of that means. Let's continue for now, and I'll come back to this. Some history. The first laser was built by Theodore H. Maiman in 1960, with a lot of help from a lot of other researchers. It was made using a ruby, and it actually had a decent amount of power to it. He said that it had the power of 1 Gillette. Really weird term, but what he meant by that was it was powerful enough to burn through 1 Gillette razor blade. Kind of crazy, eh? This actually started, and he learned a lot about how this worked before from Albert Einstein back in 1918. He produced the hypothesis for how a laser might work. And although laser is what we typically talk about, the first similar scientific instrument to this was actually called a maser, and it was produced almost 7 years before that. M standing for microwave instead of L standing for light. So the same thing was produced, but in a microwave. Very interesting there. Let's talk about what lasers are used for. This is a plethora of things, right? They are used from very small instances. You see them in the classroom every day. In fact, you probably see them every day, different aspects of your life. We'll talk more about that in just a second. But they can also be very dangerous. You see Star Wars, right? And they're burning through doors and ships and everything in between. We'll talk about what parts of that are true and not true as we go through this. This is an instance where we might see a laser almost every day. Lasers are used trillions of times a day to record barcodes in grocery stores, in warehouses, in freight shipping, in libraries. Basically, anytime you're moving a box or material around and it needs to be recorded by a computer, a laser is used to read a barcode. Super powerful technology. It's actually changed the world in tons of ways. This saves hundreds of thousands of hours of recording and documenting where things go because it can all be done by computers. We just needed a way to read it and enter the laser. The same types of lasers are actually used for safety all over the world. It can protect the garage door in the case of implements being in the way, but it can also protect a person. Garage doors have a lot of weight to them. And so if a person is in the beam of the laser, the garage door will not close. It protects a lot of people. Lasers are used to transmit information. Think fiber optics, think cell phones, think internet. All of that is made possible because of lasers. In fact, every time that you send a text on your cell phone or load a web page, what happens is your phone sends a signal to the cell tower. The cell tower then transmits that signal via a wire to a transmission station, which then sends a laser signal containing that information you requested or the text you're sending up to a satellite. That satellite can then bounce that laser signal to another satellite, which then beams it down to another transfer station, out to a cell tower and to someone else's cell phone or to a server where that information is stored. Without lasers, this actually wouldn't be possible because you have to send so much higher power signals, or using something like radio signals, we couldn't send enough information in a packet to load web pages quickly. The same technology can be used to direct missiles to very specific targets. This allows us to take out maybe important structures without harming a lot of people, or to make sure that missiles don't go awry and hit things that we don't want them to hit. That would be pretty bad. Now, everything we've talked to up to this point has been lasers sending a signal, very low power lasers. Lasers can be very high powered. In this case, cutting through metal and other materials. This is something that lasers do all the time to shape things. The I-beams that hold up the building you're probably sitting in as you watch this were cut by lasers. The interesting thing is lasers are really powerful up to a point, but actually any metal over an inch thick is not best cut by a laser anymore. They're best for metals that are thinner than an inch. If it's thicker than an inch, the laser tends to just melt the metal and it makes a really messy cut. So what we use for things thicker than an inch is pressurized water. Laser can be used both for cutting and changing things, and also for health and helping people have a better quality of life, right? One of the most common ways we think about that is LASIK eye surgery, but lasers are used all the time in the operating room all over the world to help people and heal people. They're also used all the time in the scientific community for things like DNA sequencing. Every time DNA is run through a laser beam, it can excite certain electrons in each base pair, and when those electrons then emit a photon that can be read by a detector, and the computer can interpret it as a specific base pair. At BYU, in our very own Iron Science Center, we have an extremely powerful laser. This is a picture of the poster outside the door. This is 2 stories below the ground level of the Iron Science Center in the basement, so it's kind of hidden away. But it uses a ton of power, 2 terawatts. For those of you that don't know what that means, me included, it means if you took all the power of all the sunlight hitting the earth at any given moment and condensed it to the size of a postage stamp, that would be how much power is flowing through this. It's actually more power than runs through the entire electrical grid of the world. Pretty amazing. For that laser to be powered up and use that much power, though, it only uses it for a millionth of a billionth of a second. It's actually only been recently that we have kind of a more sci-fi Star Wars laser beam unit in existence. This is on the USS Ponce. It was deployed only 2 years ago, and it is a literal high-powered laser that's made for shooting things down. Think like the Death Star at Star Wars, right? Ready, aim, fire, boom, and boom, there it goes. The cool thing is this is really precise. You'll actually see there's a camera on that boat that's watching what gets hit, and the laser doesn't even harm the camera because it's so precise. And so this is got amazing application for maybe knocking out the rudder of a boat and its navigation systems and its guns without ever harming a person on the boat for warfare, right? We can stop taking lives and just stop destruction from happening before it ever gets the chance to happen. All of these lasers, from super high powered ones that can blow up things to powerful ones that can send signals hundreds of miles through space, to ones that just read barcodes in front of us every day, they all work the same way, with just small differences in the power and medium that they use. So let's talk about how they actually work. Lasers run on 3 principles of light: monochromatic light, directed light, and coherent light. All lasers do this to be classified as a laser. Monochromatic means that light is a single wavelength and frequency. You can't have a reddish blue laser. It just doesn't exist. It's either going to be red or blue. The reason for this is that you have stimulated emission. Talk more about that in a second. That's the S in laser that produces all light of the same wavelength. The light that's produced is directed light. What that means is that it all comes in a straight ray, like we've talked about in class. Most light beams out. That means it spreads out in any direction. This is really evident with a flashlight. But lasers do not beam out. Lasers are not focused. There's no like magnifying glass that they run through that focuses their beam. It is directed light that does not disperse very much. Now, I say very much because over hundreds of miles, that laser light can disperse, from a millimeter in width to maybe a foot in width. But again, that's over hundreds of miles. It very much stays and follows the principles of a ray. And then the light produced by a laser is coherent. That means it is in phase and polarized. Every trough and every peak of every wavelength is exactly in line with all of the other troughs and peaks in the laser beam or the laser ray. To produce that, there are 3 parts to a laser. It's crazy how simple they are. There's an energy source, a medium, and 2 mirrors. You could seriously make this at home. The energy source, think like a camera flash bulb, except it flashes like 100 or several hundred times per second. It's just bombarding a medium with photons that contain energy. That's all it is. This medium can be made up of several different things. They can be solid state, think a ruby like the very first laser. They can be made of gas, something as simple as carbon dioxide or xenon. They can be made of dye, organic dye, or semiconductors, right? So this energy source bombards this medium with tons of photons every second. Those photons then, they lift up electrons in that medium to a certain excited level, and then when those electrons decay, they produce a specific photon, and that specific photon produced by that medium is what makes the laser light we think of. So a ruby will only produce one type of laser light. You can't change it. So the medium matters for what you want to do. And then those laser lights that are produced, those photons that are produced by the medium, are bounced back and forth between two mirrors over and over and over. And what happens is one mirror is slightly more permeable than the other. So over time, as that light builds up in power, eventually some of it begins to pass through the second mirror. And that's the laser light we see. So again, here's a picture: energy source producing energy. It goes into the medium, it bounces back and forth in the mirrors, and eventually cuts through one of them. Now, there's three processes that allow this to actually work. This is where the name laser comes from. As you bombard this laser with light, that's the L, that light is absorbed. So it's stimulated absorption. As that light is absorbed and amplified, those electrons again move to a higher energy level, like we discuss here. And that higher energy level then decays. When that decay happens, this is what stimulated emission does. This is really what makes a laser work. That photon that's produced by the medium then hits another molecule, and that molecule has an electron, and it forces that electron to drop to or decay to a lower energy state, producing the exact same photon in the same amplitude, the same wavelength, and it's in phase. And it results in this cascade. Think dominoes. One photon hits another electron that produces another photon, and away they go. And then what you have is tons of these photons bouncing back and forth between these two mirrors, escalating and escalating. The other thing is, you got to realize this energy source is going off hundreds of times a second. So even after a photon is emitted, that molecule then has its electron bounced back up to an excited level by the energy being pumped in, so that when that photon bounces back from the mirror to come back through that same molecule, it actually produces a second photon again. And so this light is being amplified. So here's a visual aid of how this works. You have some light produced, and it is forced into the medium. That medium then has its electrons move to a higher energy state. When they're excited, they then decay or emit a photon. So one off-screen has decayed. This photon can then force the decay of a second electron, producing the exact same photon. You'll notice as you're watching this decay happening, that all of these photons that go through match. They are in phase, they are in the same amplitude, they're monochromatic. And this is what allows a laser to have such a straight beam without needing any focus. And they just build on each other. There's that same domino effect again. So you've got stimulated absorption, that leads to spontaneous emission, and that spontaneous emission leads to stimulated emission. And this process is happening hundreds of times a second in your laser. There's a little bit on lasers for you. Thanks for watching, and I hope this was a great educational video for you.